So we've previously introduced Thevenin's and Norton's theorems. Now let's look at it in terms of how can we use these two tools to help us solve filter type equations or tuned circuit type equations. The use of Thevenin's theorem can simplify the solutions of some AC circuits. So if we look at this AC circuit that's given here, we've got two capacitors, or we've got one capacitor and three resistors here, an input and an output voltage. To try to do an analysis on this circuit without significantly reducing it down would be a difficult problem. So let's suppose in this example we wanted to find the voltage drop, the output across V sub C, the capacitor. If we tried to use just the trig functions for the solution, it would end up becoming very complex. So what we can do is use Thevenin's theorem to reduce the problem to a simpler circuit. And you'll recall when we talked about this some weeks ago that we went through a Thevenin's explanation of open circuits and short circuits to determine a Thevenin's resistor, a Thevenin's equivalent resistor, and the equivalent circuit. So that's what we're going to be taking a look at here. Just so you know, Thevenin's theorems are typically done with circuits that represent the input source as a voltage. Norton's theorems are typically calculated using the current and a current source. So let's take a look. This looks like a very busy slide here, but if we take a look at it step by step, it's a little easier to look at here. So the use of Thevenin's theorem can simplify the solutions to some AC circuits. For example, consider the circuit that we've got here at the top. Suppose we wanted to find the voltage drop across the capacitor. The problem, as we said before, would be fairly complex. So using Thevenin's theorem reduces the problem to a simple circuit and makes it quite easy to calculate. So if we consider that C, in this case, is the load, then the open circuit voltage and the Thevenin resistance can be found. So that's what we're going to take a look at here as we work our way through through this example. So we're going to Thevenize the circuit, find the open circuit, find the cutoff frequency, and the output voltage at that cutoff frequency. So as we've done before, we're going to create an open circuit. So we're going to remove the capacitor and we will have V open circuit then equal to V2, since there's no voltage drop then across the resistor R3. So V open circuit then equal to V2 equals the product over the sum. In this case, we're using the product of the voltage source times R2 over the sum of R1 and R2. Okay, so after we open the circuit up with this capacitor, essentially the rest of the circuit disappears and we're left with just what's going on between those two resistors. So if we short the source, shorting the source results then in our Thevenin of 6.19. So we're down here in the third configuration here of the circuit. So we've shorted the source, notice we've taken it out. Now we end up with a Thevenin's equivalent for the resistance of the 4.7 and 1.49 ohm resistors. Okay, so we've simplified the circuit. We end up with a Thevenin's resistance then of 6.19. The Thevenin's equivalent circuit then with the load connected, then the cutoff frequency can be found, and the frequency then becomes the point where X sub C equals our Thevenin now in this case. Okay, so we've reduced it down to our Thevenin and the load capacitor in this case. So from that we can calculate the cutoff frequency as the 1 over 2 pi the capacitor times our Thevenin, which gives us 1.29 kHz for the cutoff frequency. Okay, so this results then in a high-pass filter. The circuit then will pass all frequencies above 1.29 kilohertz. We can find the output voltage then at the cutoff frequency by using that Thevenin's theorem. X sub c then must equal 6.19 k ohms when we did our calculation. Therefore, V sub c equals the open circuit voltage times the sine of 45, or 3.89. Applying Ohm's law and Kirchhoff's laws, then we can calculate for the current through the capacitor, 629 microamps, and we see here that that current is equal to the current that we would have originally had up here in branch 3 across R3, I3, where C and R are both in series. So the capacitor drop across the capacitor becomes I3, R3, and we get a output then of 2.96. So in a circuit then shown, we've got a little bit simpler circuit here. The output voltage then and the cutoff frequency can be found now using a Norton's theorem. Okay, in Norton's theorem, you'll notice here that we've got a source, and then down here we've switched to a current source, so voltage to current. In this case, we're going to use the conductance equivalence, and the idea here is we're using those reciprocal relations we learned in the previous chapter. So we're going to find the cutoff frequency and the output voltage at that cutoff frequency. So I short circuit in this case is equal to E over R1. So what we're going to do is create a short circuit. We're going to take the capacitor out. We're going to create a short circuit then at the output, and we end up with a short circuit current of 4.44 milliamps in this case. So the conductance then for the network, or the Norton's equivalent, G1 plus G2, we have 370 microsiemens plus 303 microsiemens, a total then of 607.3. So we see it down here in the third representation of the circuit. Okay, so G sub n is found from that circuit. The cutoff frequency then can be calculated from the equivalent circuit, Gn divided by 2 pi times the capacitance, gives us a cutoff frequency of 5.36. So at that cutoff frequency, the I short circuit divided by the conductance gives us a V output maximum of 6.60 volts. Okay, so you can see here we're calculating from this fourth iteration of the circuit, then where we have 4.44 milliamps, and we have a conductance G sub n and our capacitor C1 at 20 nanofarads. So our output then, 0.707 times V max, gives us 4.67 as our value. Okay, when we come back, we're going to take a look at the last section here of bandpass filters. We've looked at low pass, we've looked at high pass, now we're going to look at the bandpass filter.